Good morning, folks. This is Todd Coburn of Cal Poly Pomona with Lecture 10 of ARO3271. Today we're going to be extending our look into fasteners. We're going to be focusing specifically on aerospace fasteners now and on techniques that are more common to aerospace fasteners. So let's get started. Now last time we focused on non-aerospace bolts and fasteners, how we call them out and what the strengths are. And so far, all of the work we've done has ignored the eccentricity that occurs in a joint. For example, we analyze the shear and the bearing and the tear out and the net tension for a joint like what is shown here, but we have been ignoring that this line of action and this line of action is all offset by some eccentricity. What that means is this force actually is going to introduce a moment. We call this a secondary moment because it wasn't an applied moment. It's one that sprang out of nowhere due to the geometry. So because these two lines of action, if we have relatively thin sheets with that are attached together with a fastener like this, we have a fastener here and we're pulling with some force P, we see that the distance between the two centers of these two sheets, E, this develops a moment of PE. Now, if these sheets are relatively thin, then the moment will be small. Now, if we had had a double shear joint, like say this one here, P, and this is P over 2, and P over 2 fastened together here, you see we still have an eccentricity, but first of all we will cut that force down. The moment is going to be that force over 2, and the eccentricity, then we're also going to have an eccentricity from center to center. So what this will tend to do, also because this joint is centered, and if we have another plate here, let's say this is a double shear joint like this, so this is actually P, forget this stuff. Then what we see is the load comes here, it comes out here, you get a little secondary moment, which is at least half the value of this for the same thickness sheets. And then that moment comes out when the load gets back here, there's no secondary moment anymore. So all the secondary moment is reacted where the splice plates are. But if you have a lap, that's for a butt splice, properly designed butt splice. If we have a lap splice, then we're going to introduce this moment PE, which is twice what the moment was for the butt splice. And then we also see that that moment continues into the structure and has to dampen out on its own. So it's actually introduced a new moment into the structure. Now normally if the sheet thicknesses are relatively thin, we ignore this. The reason we're able to get away with ignoring it is because if we test our joints using the same approach and ignore the moment when we test, then the shear and bearing allowables that we develop already have accounted for whatever small moment occurs. What this means is as long as our sheet thicknesses are in the range provided, you'll notice in your handbook in the allowable section that our bearing allowables, we have different values for different size sheets. Now different size sheets, the thicker the sheet is, it causes a slight change in material properties. But also, if those bearing allowables are from testing for samples that are in those thicknesses, then the values, the bearing values shown in our handbook, already account for these eccentricities, these small eccentricities. This is why we can ignore the moment, or one of the reasons we can ignore the small moment that develops due to the eccentricity, because already the shear and bearing allowables in our handbook account for those. Now the problem occurs if we start attaching thick parts together. Now if these are outside those ranges of what those bearing allowables were developed for, then that eccentricity may no longer be sufficient. It may not be reflected, like when we have a big aluminum ring attaching to thick composite sandwich with splice plates like this, we end up with eccentricities and secondary moments which may need to be addressed. So what we're going to do here, even though we typically will ignore bending moments in aerospace analysis, that really is only valid when the sheet thicknesses are relatively thin. If our thicknesses get thicker, like for many rocket parts or larger, beefier parts, then we actually need to be able to analyze the moment that occurs. Now, as soon as we start analyzing the moment that occurs, we start getting into some rather challenging detailed work as we look at the prying effects on the head and things like this. We're not going to try and learn that in this undergraduate class. All we're going to focus on is analyzing what moment springs into being and how that's analyzed in this particular class, okay? And we're still going to ignore the moment unless we have a joint where we're asked to assess the moment or it's obviously thick, okay? So for a lap splice like this, you can see this eccentricity is going to just be half the thickness of each plate, right? T1 over 2 plus T2 over 2, which is given by this little equation here. And if we have a, let's say a lug, which is kind of a special name for certain kinds of joints, you can see this is a double shear joint. So we've got P here, and they're showing it as P over 2 for each half. You can see, just imagine this thing cut in half, because actually if this is P, half of that's going to go up through this part and half is going to go down through this part. So they've already Brune has in his picture shown that we get half of that each place. You can see this first P over 2 is kind of like centered at the middle of this. So in this particular case, our eccentricity is going to be half of this thickness, right? Which is T2 over 2. And we've got half of this thickness, T1 over 2. Excuse me. This is half of the thickness, so this is half of the half, so this is T1 over 4, right? Then we have whatever gap. If there's any gap in there, we've also got a little gap. That's our total eccentricity. So if we call that gap is going to be T over 4, which is this little distance here, plus the gap, plus T over 2, then that, oh, and look at this, T1 is this little skinny guy, so this is T1, and this guy down here is T2, okay? So let me do that again. Let's say we have a joint like this, a thick joint, and we have a gap. So what we're going to do first is we're going to imagine the gap all occurs at one side. So if this is P, then this is P over 2, and this is P over 2, right? Okay, now we've got this gap here. Let's go ahead and draw this bigger. So we've got this little piece, we've got this piece, and we've got this piece down here. Now we've cheated with this gap all the way over to one side. Now if you look at this, this means this little dimension is T1 over 2. This is G, this distance in here. And this is to the center of this. This from here to here is T over 2. But from the middle where half the load is to there is T2 over 4. This is where P over 2 is centered. You've got another P over 2 centered down here. This is going down this way. You'll notice the eccentricity on this side is a little less than it is here. We're going to cheat the gap over one side. If you have a gap, it's going to tend to act in its worst fashion. So our total gap, B, is going to be T1 over 2 plus T2 over 4 plus whatever gap we had. And our moment is just that P times B over our moment then is just going to be P times B, but the force of the eccentricity is actually P over 2. So it's actually whatever the force is, which is P over 2, all of that times B is the moment. So that's what you're seeing right there. Does that make sense? So that's how we handle a gap. Okay? Let's look at it again. Let's say we've got a force here, P, and it's transferring to right here, P over 2, and right here, P over 2. Imagine that half of this force goes this way. So it's basically centered on one half. This is one half this thickness, and it's centered here at 1/4 of the thickness. So this dimension here is T2 over 4. Then we've got the gap, and then we've got this dimension here, which is T1 over 2. This gives us this equation for the total eccentricity. We're using E rather than B for eccentricity. Our moment then is the force that's transferring this way, which in our case is P over 2. And it's multiplied by the eccentricity. This gives us the total moment in that joint. Now, the moment going the other way down to this one, since we cheated all the gap to one side, there's no gap down here. So the eccentricity there down below is just going to be T1 over 2 plus T2 over 4. There's no gap there. That moment will be P over 2 times that E below. It's less. Therefore, we generally won't even check it. We're only going to imagine all the gap is on one side and check that spot. Now, once we have that moment, we can check the plate for that moment, or more specifically, we can just imagine that the fastener is carrying a pure moment, and that's a gross simplification, but then we'll just take the cross-sectional area of the bolt shank, and we will analyze it for the bending MC over I, where we have the I using that moment and the I of that bolt and the radius of the bolt, or D over 2 of the bolt. See how that works? When we need to analyze, when we have thick parts being clamped together and we're asked to look at the bending moment in there, then that's what we're going to do. We're going to calculate the eccentricity. We're going to calculate the moment based on that eccentricity, the worst eccentricity, and then we're going to analyze the bolt as if it was in pure bending. Now, if the bolt is also in tension, then we will have to superimpose those two stresses to get the total stress. And if the bolt is in shear, in some cases we will need to also do an interaction equation. Okay? In other cases, we'll just look at those two separately. Okay. Now, next we'll look at some aerospace standards. So for bolts, so we're going to be seeing for aerospace, we're going to use a lot of rivets. We're going to use a good amount of high locks and lock bolts. And then we're going to use some threaded fasteners. Threaded fasteners, we have to take extra care that they don't come unthreaded in flight. There's 3 major standards that we're going to analyze for threaded bolts. And then we're going to look at how to combine loading on aerospace bolts. And the combination of loading for the threaded fasteners used in aerospace will be the same as we will use for non-aerospace fasteners. So last time we looked at aerospace non-aerospace standards, but today's study on how to interact our loads on the bolt to calculate the net effect of for the margin of safety is going to use the same approach as what we're going to look at here. So there are various bolts. We're going to basically break our bolts into a few major classifications. Let's take a look at that on the next slide. This is just some information on nuts. We're not going to do much with this. That's just for some design help. Okay, the first kind of bolt we're going to look at is a Army-Navy steel bolt, an AN steel bolt. This table here gives us the allowable based on the diameter. Now, based on these nominal diameters, you can calculate the shank area, but it's provided here for you if you want to use that. Then we see 3 allowables. Notice these are not stress allowables like we normally see. These are force and moment allowables. We need to be a little bit careful because often when we're talking about bolts, sometimes we'll talk stresses, often we'll talk forces. So these are the allowable forces, or the ultimate allowables. S sub U is the ultimate shear allowable. That's how much shear force the bolt can take. P sub U is the tension allowable. That's how much tension the force the bolt can take. And the moment, M sub U, is the max moment it can take. For example, let's say that we have a 1/4 inch bolt. If we have a 1/4 inch bolt loaded in tension, we look and see we got a 1/4 inch bolt. We know that our allowable is this. If we have a tension load of 2,000 pounds, we can write the margin of safety directly. If instead we have a 7/16 bolt loaded in shear, let's say 8,000 pounds of shear, we can just write the margin of safety based on that allowable. Our margin of safety is 11,275 divided by the 8,000 pounds minus 1. Let's say instead we have a 5/8 bolt and it's subjected to a moment because of that eccentricity, and the moment is, say, 6,000 inch-pounds. Well, we'd look here and we say, oh, this is only good for 4,320 inch-pounds, therefore it's going to fail. It's going to have a negative margin of safety. If instead we have a bolt that has, let's say, shear and tension, these are the two allowables, we then are going to have to use this interaction equation. Since we have shear and tension, we're going to have to write the stress ratio for both. What this means is we would have to then go and write we'd have to say, okay, let's say that we have on this 7/8 bolt, let's say the shear force is 5,000 pounds, and the moment is 2,500 inch-pounds. Okay? Now in this case, we'd say, all right, our stress ratio for shear is just going to be 5,000 divided by the allowable 45,099. The stress ratio for tension, or excuse me, for the moment affects our tension stress. So that is going to be our moment, which was 2,500 over 11,850. And in that case, we now have to apply this interaction equation. Now, we don't have a closed form equation, so we're going to have to go to the interaction curve for threaded fasteners, which looks something like this. We'll look at that on the next slide. This is going to have RS down here and RT down here. We're going to plot our point, draw a line, and write the margin of safety as we learned to do in ARO3271. Let's say instead that we have a 1-inch bolt. Let's say that 1-inch bolt has an axial force of 30 kips, a shear force of 20 kips, and a moment of 5,000 inch-pounds. We're going to first write our stress ratio for tension. Now remember, tension is going to, the normal stress is P over A plus MC over I, right? So actually we can write that tension stress ratio as the ratio of both. So we've got the axial one, 30K over, let's see, that was axial, so our allowable is 80.700, right? 80.700, plus we've got the moment one, which was 20K divided by 17.670 inch kips, right? That's our total stress ratio for tension. Then we get our stress ratio for shear, which we said we have 20 kips, and our allowable is 58.905 kips. Now we've got our two stress ratios. The tension stress ratio combines axial and moment. The shear stress ratio is just the shear. We're going to take those two stress ratios, plot them on our curve, and write our margin of safety. The interaction curve is on the next slide, or in a moment we'll take a look at that, okay? That's how we do that. Got that? So if we only have a single force on the fastener, we don't need to calculate stresses. Since we have force allowables, we can write our margin of safety directly against those, the applied force versus the allowable force. And if we have only a single load, like shear alone, or axial force alone, or moment alone, we can just write the margin of safety directly from those two numbers. If we ever have a combination, now if we have axial and moment, we can once again just add those two stress ratios and write the margin of safety directly. But if we have shear with either axial or moment or both, then we're going to have to write both stress ratios and use the interaction curve. And the same approach will be used for all threaded fasteners. The difference is that we will have different allowables. Okay, so this is how we combine them. This first equation is showing if we just have tension and shear, we can combine like this. If we have tension and bending, you just add those together, write the equation like this. We don't actually need to write the equation. All we're going to do is calculate our stress ratios. As I said, once we have the stress ratios, we'll take the shear stress ratio on this axis, plot it against the tension stress ratio or the normal stress ratio. We're going to draw a line from the origin through that point and then write the margin of safety as we learned to do in ARO3261. Got that? If you don't remember how to do that, pull up your ARO3261 handbook and review. Okay, oh, one more deal. These AN bolts, these dash, a lot of times they're called out as a dash number, like AN 8 and such. That 8 or whatever is the number of sixteenths. So 8/16 would be a half-inch bolt and so on. So Brune has some, calls these out with using their dash numbers. Sometimes I will do the same thing. If that happens, that's how you convert that. All right, the next kind of bolt is an internal wrenching bolt, a steel internal wrenching bolt. Steel internal wrenching bolts have the same interaction curve as we saw. In fact, all threaded fasteners have the same interaction curve. It says here it's an AN bolt interaction curve, but really it's for all threaded fasteners. And you can see from our table here that we have a shear, moment, and axial load allowable. We're going to handle these the exact same way. If we have a 2024 aluminum bolt, what we have here, we have the same threaded fastener interaction curve, but you'll notice we have different allowables. Now what this is providing is not force allowables, but stress, this is again force allowables, but what we have is our, this is the force allowables for it's a 35 KSI shear bolt, 62 KSI axial stress, and these are the force allowables. So this is the shear allowable in pounds, the axial allowable in pounds, and the bending allowable in inch pounds for those, okay? And we're going to use the same interaction curve. So that is how we handle threaded fasteners. If we have a non-aerospace bolt, we will take the allowables from last lecture, write stress ratios in the same way, and use the same threaded fastener interaction equation to combine those stresses, okay? Next, we're going to look at a different kind of fastener. These are lock bolts. So lock bolts are very commonly used in aerospace. They're permanent fasteners. Basically, they're a fastener that's designed to be put in place, and when you apply the collar, it breaks off the back end, so you have a permanent collar on it. In order to move these, you have to drill them out. It's a big hassle, but they're done a lot. I've got a number, you'll notice a number of links in the PowerPoint. I'm going to encourage you to pull up those links and watch these videos. It really helps to understand the way these lock bolts work. Okay? This is a synopsis where you'll put the fastener in, you'll put the collar on, you will then apply a tool which presses that collar on. As it does, it squeezes the collar down onto the threads. If the threads are like this, it squeezes the collar until it deforms the material into the threads. The videos show this really well, and you can and until it breaks off. This video right here, these two videos I recommend watching. Watch it and then stop it and go slowly through as you see how that tool presses the material, takes the material and deforms it and jams it down into the grooves of the part. That's how these things work. Now, that's just to help you understanding. What we're going to do is analyze these. So what we need are the allowables. These are the allowables here. Now, this little table is a little confusing unless you pay attention, and I have found that students often don't pay that much attention, so that means it might hamstring you also. This is really kind of two tables. We have this table. This is for steel fasteners, right? And we have another table, which is this one, which also has this part, okay? So the first one is for steel. If we have a steel fastener, we're going to go to this first part of the table. If we have an aluminum fastener, we go to the second part. Now, the easiest one is aluminum. You'll notice we only have aluminum, aluminum allowables for tension style heads. Now, what happens is, if a fastener is designed for tension, it tends to have a deeper head. If it's designed for shear, it may have a really thin flat head. The thin flat head holds that fastener in place, but it doesn't give as much strength. That head can break off like we saw with the button back in 3261. So we need to be alert for tension and shear type fasteners. Now you'll notice in this table for aluminum fasteners, lock bolts, all we have is a tension style head. So we're going to assume that any aluminum fastener has these allowables. You'll notice this first column is the shear allowable, and this second column is a tension allowable, okay? Now, when we get to steel fasteners, we're going to use this other part of the table. Let me erase everything and start that over. We're using this part now. So we're going to say, oh, we have a steel fastener. That means we're over here, and that means we're going to go and take our diameter, and then we're going to be looking for an allowable. We're going to say, okay, if we need the shear strength, we're going to use this column. So a 5/16 fastener has a 7290 pound shear strength. That same fastener, if we're looking for the tension strength, we're going to have to first determine, is it a tensile style head or a shear style head? Once again, the head means that a shear head tends to be very flat, like this. So if this bolt is in shear, then if it's in shear, you don't have to worry about this. But if it's in tension, you're going to tend to bend the head like this if it's very thin. A tension style head will tend to be thicker, so if it gets axial load, it has more shear and moment capability so that it can develop the full strength of the fastener. So for steel fasteners, first we have to figure out, okay, the shear allowable will always be from this column over here. The tension allowable will be one of these two columns. You've got to say, do we have a tension style head or a shear style head? If it's a tension style head, this is our allowables. If it's a shear style head, these are our allowables, okay? That's important. All right. Now, once we have understood that, we're going to find out we have now a shear and a tension allowable. Now, if we get combined load, if a fastener takes both shear and tension, then we're going to use this interaction equation, which means we need this curve, which means we're going to write our stress ratios for the axial load and for the shear, and then we will plot our point and write our margin of safety using this interaction curve. Okay? If we have an aluminum lock bolt, then we need to use this interaction curve because it has a different interaction equation. So for threaded fasteners, we're going to use the interaction curve from the prior slides. If we have a lock bolt, we're going to use one of these two interaction curves with the allowables from the prior slide. Got it? That's how we're going to do that. Now, when we get to rivets, we're going to have to be a little bit careful. This is a little summary of some different types of rivets, and it shows some relationships between like the head height, the head thickness and height versus the diameter of the rivet. We're going to be looking at three kinds of rivets: protruding head rivets when the head sticks out, and flush head rivets. With flush head rivets, we're going to have two types. One is called a machine-countersunk, which means somebody came along and they said, all right, we've got two sheets of material and we're going to fasten them together. First, they will drill the material like this, and then they will install a flush head fastener like that. That's called machine-countersunk because they machined this cut. That develops one set of allowables. If we have a fastener that has a head that sticks out of the joint, like this one, that's called a protruding head. This is our first type. This is our second type. The other type of dimpled is when our sheets are really thin, so they're too thin to machine. What they will do is dimple it, which basically means they'll take that flush head rivet. They'll use a tool to take the sheet. They'll take the sheet. We got two sheets attached together here. They drill a hole through it, and then they apply a tool which bends the sheet into this form. And sometimes they do this as they're installing the rivet. Then what they do is they apply this rivet, this flush head rivet. So now the rivet ends up they didn't make the sheet thinner at all. It's just deformed at the place where it's joined. You can do that with a double dimple where you dimple both sheets, or where you only dimple a single sheet and maybe machine-countersunk the other sheet as shown down here, okay? We're going to treat both these kind of rivets as the same. We're going to just call these dimpled. We're going to call this machine-countersunk or just countersunk. We're going to call this protruding head. So we're going to get three different sets of allowables for rivets. It's going to be important that you can carefully navigate through that and get the right allowable using the approach. It's going to feel kind of convoluted for you, but this is the way it's often done in industry. this little video down here, this link, you can click on that or type that into your browser. This is also another really good video for understanding how rivets work. All right, if we have a protruding head rivet, we're going to have a detailed approach to get the allowable. We're going to need a shear allowable, and we're going to need a bearing allowable, and we're going to need a tension allowable a lot of times. For the shear allowable, we're going to start by getting like a pristine, perfect allowable, which means we're going to come to this table. We're going to look for the material of our rivet, that's leftmost column, and then we're going to come over and look at the rivet size. So we're going to say, all right, let's see here. We have a let's say our rivet material is 2017 T3. Now watch out, some of these look almost identical. 2117 looks just like 2017, and 2017-T3 looks kind of like 2017-T31, so don't get fooled, all right? So we're going to go here. Next we're going to go over here to the rivet diameter. Let's say we have a 3/16 fastener, so that means for a 2117-T3 rivet that's 3/16 diameter, our S sub B prime, or our perfect allowable, we can call this, I didn't really call it this way in the handbook, but we could say it, our shear allowable prime, because it's the uncorrected value, is 1090 pounds. Now that's not the final value. We're actually going to have to tweak that. Mill Handbook says that we're supposed to tweak this number using this slide here, these two charts. What I would like you to do is not use these tables at all. We're going to use this equation. So first we're going to get S sub B prime, and then we're going to calculate the S is equal to R sub C times S sub B S prime. And that's going to be our shear allowable. This is our ultimate shear allowable. So basically we're going to take the diameter to the thickness ratio in this equation. If we have single shear, we use this equation. If we have double shear, we use this equation. So to get our rivet allowables, we're first going to come here to get S prime. We're then going to either use the single shear or double shear ratio, R sub C, to calculate how to correct that value. That will give us the allowable shear allowable for our fasteners, okay? That's our approach for rivets. Now that only gives us the shear allowable. We then need to get the bearing allowable. We're going to have kind of a convoluted approach for that too. Let's look at that on the next slide. So if we have bearing, so this is called a unit bearing chart. What unit bearing means is this is the bearing allowable if our sheet material had an FBRU of 100 KSI. Now you'll notice very few of them do. Most of them have a higher bearing strength. So what you're going to do is go look up for your sheet material, what's the FBRU for the sheet material. You're then going to calculate a ratio of the FBRU of your material. Let's say we have 132 KSI material, and that means our ratio is 132 divided by 100K. So our bearing allowable, BRG, we could say our bearing allowable prime is going to be whatever we find here. So if we have a, let's say we have a 3/16 rivet in 050 sheet, that means this is our allowable. Our pristine allowable is 955 pounds. We then go and look up the bearing allowable for our sheet material. If we found out it was 132 KSI, we would write this ratio 1.32. Our actual bearing allowable then is going to be S bearing prime times R, which means it's 955 times 1.32, and that is now our bearing allowable. S allowable. If we have a shear of say 500 pounds, we could write a stress ratio against bearing and a stress ratio against shear, which we got the allowable from the prior slide, and that would tell us what our allowable is. For example, let's say we have a fastener. Let me do this a little more. Let's say we have a joint like this, and it's loaded with a force P, okay? Let's say this force is 500 pounds. What we're going to do is we're going to first go and get our, for shear, we're going to get our S prime. We're going to take that S prime and we're going to calculate our RC. We're then going to multiply those together to get our S allowable for shear. We're then going to go look at bearing. That means we're going to get our S prime, which is just the value from this table. And then we're going to get our R, which is this ratio. We're going to apply those together to get our S allowable for bearing. This was the allowable for shear, this is allowable for bearing. Whichever one is smaller is what controls. So our margin of safety is going to be S allowable, whatever the smaller one is, over our applied shear minus 1. If I ask you for the margin of safety for bearing, then you will use this allowable to calculate the margin of safety. If I ask you for the margin of safety for shear, you will use this allowable against the applied shear. If I ask you for the critical margin of safety, you will check both of these and report whichever margin of safety is smallest. Now this is how we handle fasteners. Now you've got to be careful because this is all valid if there's no tension on the rivet, which is generally the case. If there is tension, we have to take one more step and we will have to use an interaction equation to combine tension and shear. Okay? So if we have only shear, we're going to need to check two allowables and report the margin of safety on the minimum value. If we have shear, if we have only tension, you can use an approach I'm going to give you in a minute. If we have both, we're going to have to use an interaction equation. I'm going to talk about that next. If we have, now before we talk about tension, if we have a machine countersunk bolt, actually you don't need to overwrite this table because your book has been corrected. That was a semester ago or something when I had a typo in there. If we have a machine countersunk rivet, so it's countersunk, and most countersunk rivets are machine countersunk. So if we just say it's countersunk, we're going to assume it's machine countersunk. Only if we say that it's dimpled will we assume that it's dimpled, or if we can see that it's dimpled. If we have a machine countersunk rivet, we're going to have a little simpler approach than with the protruding head. What we're going to do is come to this table here, and we're going to use this table for everything. You'll notice we have rivet material. So first you're going to find your rivet material. It's either going to be this, this, or this. We've got no other allowables in this class for machine countersunk fasteners. So our rivets, we will only have rivets of one of these three types. So first you look at the part of the table that has the right allowable. Then you're going to go and find your diameter. If we have a 5/32 fastener, we're going to be here, 2117T3. Then you're going to look at your sheet thickness, and let's say we have 063. That means we had for our 5/32 fastener, we have an allowable of 523. Now notice this table has no values up at the top for this column. That means this fastener should not be used in anything thinner than 025. If we have it in a thicker part than 0.09, what we're going to do, anything beyond 0.09, we're just going to use this value, okay? The value down here is the shear strength. So what happens is, if we have really thin sheet, then the sheet will have a smaller bearing allowable than it does for shear. That means the shear allowable is irrelevant. If you want to know the shear allowable for this particular rivet, it's right down here in the lower column, in the lower row. This is the shear allowable for these. But if we have thin sheet like 032, then it will never get to that full shear strength because it will first fail in bearing. That's what we see in the chart. So this chart is giving us, these are all bearing allowables, okay? All of these. What this down here is the shear allowable. Now if we get a sheet thickness that's between two of these values, like we have 070 sheet thickness, then we would have to interpolate between the two values provided. If we have a sheet thickness greater than the last entry, we will just use the shear allowable for anything greater than that. So if we have 090 sheet, we'll use 575 for a 5/32. If we have 091 or greater, we'll use this 596. That's the approach we'll use in this class. Got it? Once again, we may have to combine with axial load if there is axial load. Okay. If we have a dimpled rivet, we're going to use this table. This table is like the last table in that you will see that the lowermost row has the shear allowables for these. Okay? See these down here? These are the shear allowables. If you need the shear allowable, that's what it is. Okay, we've got 3 types of material again, and for those 3 types, this is the rivet material, and then you're going to go, let's say we have a 2117T3, you're going to go and figure out which of these sheet types is most appropriate. This type, then we'll use these columns. This type, we'll use these columns, and so on, okay? That's how this is read. These are the bearing allowables, and we won't exceed the shear allowable. So anything beyond the last entry will be this lower value, and we're not going to use them for smaller values, okay? So that's how we get bearing allowables of dimpled rivets. Now, if we have tension on a fastener, we're often not going to, but we might in this class to help you learn how to do it, then we're going to have to get a tension allowable. So we've got 3 tables for that. We've got 1 for each type of rivet. These are grossly approximate numbers, but if we have a protruding head rivet, we will use the first table. So this table, if we have protruding head rivet, we'll use this table. If we have a machine-countersunk rivet, we'll use this table. If we have a dimpled rivet, we'll use this table, okay? Now you'll notice this is for a certain kind of sheet. We're going to ignore that and use it for everything. This is the only value we have. This has a set of values. If you're between these sheet thicknesses, you're going to need to interpolate to get the correct tension allowable. So let's say that you have tension on a fastener. If you have tension on a fastener, and if there's no other loading, all you got to do is take the tension on the fastener, find the allowable for your fastener, and you can write your margin of safety as simply the allowable tension divided by the applied tension minus 1. However, if you have tension and shear, what you would have to do is first calculate your shear allowable. And we're not talking bearing now, we're talking shear. If you look at your fastener, bearing is applied to the sheet and to the side. It's not interacting on the same surface. If you have shear and tension, those could interact. So we're only going to combine our shear stress ratio. So you're going to get our shear allowable. You'll write your stress ratio for shear. You then get your tension allowable. You'd write your stress ratio for tension. You then take your tension stress ratio and your shear stress ratio. You plug them into this equation. Now you'll notice we don't have to use an interaction equation because this is our, we don't have to use an interaction curve because our interaction equation has a closed form margin of safety. So if we have tension alone, we can write our margin of safety directly. If we have tension and shear, we need to first calculate the shear allowable, then calculate the tension allowable, then combine those two, write the 2 stress ratios, and get our margin of safety from this equation down here. The same thing is true for machine-countersunk and dimple rivets, okay? We calculate the shear allowable and the tension. Now, we also will need to check our bearing allowable, our shear, SBRG. We're going to need to get our shear allowable also, our bearing allowable. We also need to write a margin of safety against bearing. Bearing might be critical. Probably this interaction of tension and shear will be critical. So we're going to need to check both. Now bearing does not interact. This equation is for tension and shear, not bearing and shear. So we will check our bearing margin of safety, and we will check the interaction of tension and shear. So our first step, anytime we have tension, is to check. We're going to get a stress ratio for shear. We're going to get a stress ratio for tension, and we're going to get a stress ratio for bearing. Okay? We can take these two together and plug into our interaction equation to get our margin of safety. And we can take this one acting alone and write a margin of safety directly. Whichever margin of safety is smaller is the one we will report as the critical margin of safety. Does that make sense? This slide gives a number of conceptual questions with their answers. It'll be useful for you to look through each of these and work through them in your handbook. Read the question, look in your handbook for the answer, and then look to see if your answer coincides. This will be very useful for understanding this. If you have any more questions, call into our Zoom session. We'll talk about it there. Good luck. That's all I've got for you. Enjoy.